Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. I am Kalyana Velvolu with the School of Electronics Engineering. In the last week, we discussed on system performance. We analyzed the effect of disturbance on the steady state error performance. In this week, we're going to apply this concept for a couple of problems and try to analyze how the disturbance affects the steady state error performance. So, this is week 9 part 2, the last part of system performance. So, the outline for this lecture will be the system performance with disturbance. So, this is from our last class. What we analyzed in the last class is when you have an input, when you have a disturbance. The system performance depends on both the input and the disturbance. So, if we have these two components, the input provides a component to the output and disturbance also provides a component. The output due to the disturbance is completely the component we do not want. So, the error component that we get because of the input is R of S minus YR, but the error component we get because of the disturbance is the output that we receive because of the entire output we get because of the disturbance comes into the error dynamics. So, that way you have ED is equal to minus YD of D. So, we have analyzed also another example in the last class. So, what we analyzed is when you have R, Y, and then we analyzed for when R is a unit ramp and D is a unit step, we analyze the steady state error performance. So, the error will be the sum of both the error due to the actual input plus the error due to the disturbance. So, the error due to the input is normal, limit S tends to S into ER, you can measure ER, plus error due to the disturbance is actually the output due to the disturbance. So, S into ED, that is S into YD. ED and YD are, there is a confusion for many students, because what is error is you have an input, we have an output. The difference between input and output we call error. However, when you make input 0 and the disturbance is acting on the system, the whole output is equal to the error. So, that is the reason your ED is equal to the output due to the disturbance YD. So, we substitute and then we can actually identify the error expression for ER of S from the K velocity, because the input is a unit ramp, we get is 1 by K. So, that is what we discussed in the last class. So, for the disturbance, when we are dealing with disturbance, very important, select R equal to 0, make this one 0 and find the transfer function between D and Y. So, I change the transfer function, this becomes feedback. So, this minus goes here. So, you have a different transfer function. So, that is the transfer function will be YD to D, the output due to the disturbance. So, I get the transfer function. My D is given as unit step. So, I get a unit step. So, then I can calculate steady state error is 1 by K. So, E with respect to disturbance is minus YDSS is equal to minus 1 by K. So, because we substitute YD of S, because our error due to disturbance is minus YD of S, so it is minus 1 by K. So, what we analyze is the steady state error for the input when disturbance equal to 0 is 1 by K, and for the disturbance when for the error due to disturbance is minus 1 by K. So, the total error surprisingly is 0. The point is disturbances are unpredictable. Disturbances can have positive step, negative step, any step, small step, no value, we do not know the value, but anyway we are analyzing for unit step. So, getting 0 is very fortunate, because the error due to the input is cancelled by the disturbance, means the disturbance is helping the system perform, which is impossible in real world, it never happens. So, if suppose if the input magnitude is negative step, then your output will be 2 by K. So, based on this one, we can understand that disturbance always have negative effect on the system. So, if we have K, from the design we can understand that K influence the error dynamics. So, select a proper K. So, if you select a good K value, high K, so then you can make the value less. So, selecting a proper K, I can ensure that my error is either small. So, this way we can actually control the error and we can also find the effect of disturbance. In the PID controller, we will again visit this problem and we will learn how to make the error dynamics 0 even when you have a disturbance by employing a PID controller. This is a simple controller K. We haven't learned the controllers yet, but we will learn in the PID section. So, now we go to a new example. So, the new example what we have here is a simple feedback control system. We have a controller GC, system 1 by JS, disturbance and input. So, it is asked, what is asked is design a suitable controller SK1 plus K2 by S to eliminate steady state error due to disturbance DFS and ensure at the same time ensure stability of the closed loop system. So, in this problem I have two objectives: to find K1 and K2 such that this disturbance becomes 0. Although I have a disturbance, I want to ensure the disturbance value is 0. Not, I want to ensure this disturbance has no effect on the output. Although I have this disturbance coming into the system, it should not have much effect on the system error dynamics. That means the system should not be able to influence the output. So, eliminate the steady state error due to the disturbance DFS. So, I want to eliminate the error due to the disturbance. So, this is one important, this is a very common problem. In many practical systems, we have disturbance coming in. This disturbance can be like a turbulence in an aircraft, because when the aircraft is flying, it encounters turbulence, it loses its altitude, and then the pilot corrects to get back. So, maintaining the altitude is most important for aircraft, because when aircrafts are in the taxi mode, so each aircraft is given selects a different altitude, safe. So, they do not go at the same altitude to avoid collision. So, they go at different altitude. If aircraft loses altitude, it can be dangerous as well. There are flight accidents happen because when the two flights are flying, one actually because of turbulence increase, one decrease. So, there can be collision as well. So, disturbance, reducing the effect of disturbance is very important in many applications. So, anyway, we have to try to analyze this one. So, whenever we try to solve any problem, we always look at the steady state error issue as important. Now, I want to analyze the effect of the disturbance. So, for the first, we would like to solve the first step. So, take the system, but we are trying to analyze the effect of the disturbance. So, what do? Reformulate the problem. So, reformulate the problem is D of S becomes the input, Y is output, R of S will be 0 like superposition. Select R of S equal to 0 and redraw the block diagram. So, I have D of S, I have ID of S, 1 by Js, GC of S. So, now if you look at this one, the output due to this disturbance is something we do not want. So, once I reformulate, we formulate the transfer function. So, let us select because steady state due to disturbance D. So, I choose to be because it is not mentioned about input. So, I can try to select a unit step disturbance. So, if it's nothing is given, you can select a unit step, because unit step is the first order input, easier. If you select ramp or parabolic, analysis can be very hard. So, when the problem does not specify the type of the input, always choose disturbance input. So, I choose the unit step disturbance, D of S equal to 1 by S, and then I can actually find my transfer function. From the transfer function, I can actually find the YD of S later. First, formulate the transfer function. Formulate transfer function YD by ds, I can get S into this nice standard second order system. Take the unit step disturbance 1 by Fs, and then I can find the disturbance, I can find the steady state of the dynamic. So, what is YD? Transfer function into 1 by S. So, take YD is equal to the transfer function multiplied with the input 1 by s. So, then my steady state error due to disturbance is limit s tends to 0 s into yd of s. So, that is equal to limit s tends to 0 s into s by j square plus s k1 plus k2 into 1 by s. So, coming back, we are not finding the error, we are trying to find the steady state output due to disturbance input. I want to find yd of s, and this yd of s is limit s tends to 0 s into yd of s. So, limit s tends to 0 s into yd of s is transfer function into the disturbance. So, once you select this one, you can clearly see that this will be 0 only when k2 is not equal to 0, because this s gets cancelled, and when this s gets cancelled, I have s by this expression. When s tends to 0, this term is 0, this term is 0, this term is 0. If k2 is not equal to 0, the value will be 0. If k2 becomes 0, I get 0 by 0 not defined. So, this expression, that means this error can only be 0 if and only if k2 is not equal to 0. If k2 is equal to 0, I get 0 by 0, which is difficult to define. So, the steady state error, the steady state value of the output due to the disturbance will be 0 if k2 not equal to 0. So, selecting k2 not equal to 0, I can ensure that the output, the steady state output due to the disturbance is 0. That means even I give a step disturbance, the output corrects after some time. This is about steady state. So, the steady state error actually is 0 if k2 not equal to 0. Now, the disturbance we solve. The first problem, eliminate the steady state error due to disturbance. We solve this one, we identify that when k2 not equal to 0. So, the first point is done. Now, what is the second condition? The same time ensure stability of the closed loop system. I have to also ensure the system is stable. So, if you are talking about stability, we are not talking about the disturbance. So, when you want to analyze the stability of the system, take the closed loop of the regular system. So, the regular system is R to Y, treat D equal to 0, take D of S equal to 0. So, choose is equal to 0 and then formulate the transfer function. So, I can formulate the transfer function by selecting for R of n. So, Y of R by Y due to R, because you have two inputs, I specify as YD of S due to disturbance, and due to R of S we specify as Y into R of S. So, by taking these two separately, we actually solve these two conditions in a separate. So, YR by R of S I get as G of S by S. So, I can formulate the nice transfer function. Now, coming back to this problem, how can you ensure stability? Stability, you have to formulate the Routh array. However, very simple. If you want the systems to be stable, you know that the coefficients J, K1, K2 has to be 0. Here, I have the term, the denominator transfer function, closed loop J square plus SK1 plus K2 equal to 0. This is our characteristic equation. J is a physical constant. Physical constants are not negative. J is always greater than 0. So, if the system has to be stable, all the coefficients should be positive. That means K1 is greater than 0, K2 greater than 0. So, very simple check. You can solve the Routh array, but you can also make directly. For the stability, we need K1, K2 greater than 0. It's because J is greater. And the steady state error with respect to ramp reference input is 0 as the system is type 2. Now if we actually see what is the type of this system. So, you have controller S K1 K2 by S, you have 1 by Js. So, S K1 K2 by S into 1 by Js. So, you see I have 2 poles at the origin. 2 poles at the origin, the system is type 2. So, type 2, we know that system type 2 gives 0 steady state error for unit step and also 0 steady state error for unit ramp, and gives you constant error for parabolic input. So, this we can easily observe. So, from that we can also ensure that the steady state error with respect to unit ramp or ramp reference is 0 as the system is type 2. So, in this way we can actually try to eliminate the steady state error due to disturbance and also ensure the stability. Means we designed. So, if you understand, this is the first time you are actually designing a controller. So, this you will learn later that this is like a PI controller. So, you will understand later, but now the PI PD controllers you will learn after the midterm examination. So, which we are learning. So, the steady state errors, then we learn root locus, and then we learn the PID controller design. Now, let us move on to a new example that is similar to our last example, but it is a different problem. So, look at this problem. Consider the simplified satellite altitude control problem shown in figure. Determine the effect of Kp and Ki on the step disturbance W, on the step disturbance input W of S. So, now if you look at the system, we have an input, we have a controller Kp plus Ki by S, and then we have a summing junction here and a disturbance entering into the system and a system. So, if you look at the system here, what is asked to identify is what is the effect of Kp and Ki on the step disturbance W of S. It did not ask about solving anything, but it is asked, the problem is asking to solve to identify the effect Hyoga Kp and Ki on W of S. So, the effect of what happens if I select some value for Kp, what happens if I select some value of Ki, something. So, it is also like some stability, but not about stability, but we are actually looking into the effect on the disturbance input. So, now again it is about disturbance. So, what you need to do, it is not with our input, but with the disturbance. So, we do not need to bother our input. So, take R of S equal to 0, use R of S equal to 0 and then reformulate the transfer function. So, reformulate the transfer function is you choose W of S as the input and then you get 1 by S into S plus 10 and then Y of S, and then all your feedback goes here Kp plus Ki by S, and then it actually goes into this one. So, plus minus. So, you will have this kind of transfer function. So, then identify the closed loop Yd by W of S, identify the closed loop transfer function. So, you will have the Kp and Ki in the affecting the system properties. So, you have the characteristic equation in this form. The question is we are more interested in Kp Ki affecting W of S. So, this specific issue is not about any other aspect, only about Kp Ki. So, now we have several cases here, because we have to solve this one, we need to also look into the various scenarios. That means, we are trying to find the error dynamics, the steady state error due to the disturbance Y of S for various cases, for various Kp and Ki. So, if you look at this problem, we have several cases here. So, the several cases are case 1, case 2 and case 3. So, the step disturbance depends on 3 cases. Cases is for when Ki is not equal to 0, any Kp, when Ki equal to 0, when Kp equal to 0, when Ki equal to 0, Kp not equal to 0. So, there are various cases we are looking into. So, we will try to first formulate the condition for the error dynamics and then observe for various combinations of Kp and Ki. So, but anyway, first formulate the steady state output, the disturbance, its limit S tends to 0 for the step disturbance into 1 by S. So, you can actually find. So, when Ki not equal to 0, and for when k not equal to 0 for any value of kp, because if k not equal to 0, just like we analyzed in the last problem for this transfer function, you will get equal to 0. That means if ki is not equal to 0, we do not get any error. That means the output, the steady state output due to disturbance is 0. That is really good. Now, the other cases is when k equal to 0 and kp equal to 0. When both are equal to 0, your YDSS becomes infinity, it is useless. So, when k equal to 0 and kp is not equal to 0, we get some constant error for a by kp. So, if you see when k, kp are equal to 0, that means there is no controller, this becomes 0. So, it obviously gives infinite error because the transfer function will be 0. So, that is a useless condition. So, when k equal to 0, kp not equal to 0. When k becomes equal to 0, the system becomes a simple kp controller, p controller without this term. So, then you will have a constant error. So, when ki is not equal to 0, it does not, for any positive value of kp, I can get this one. So, for stability, that is a different scenario, but these three ensure three cases. All the three cases will have different results. So, for different values of ki, kp, we get different steady state errors. Then, what is the relation between kp and ki and how it affects the stability is also very important, because in order to get some value of the error or in order to analyze the steady state error performance, we have to ensure the system is stable. So, that is why even for this kind of problem, we also need to analyze the stability, because for the stability, it will tell us what gains for kp and ki the system is stable. So, that is the reason, not only for this range, I also want to know when the system is stable. Otherwise, if the system is unstable, this analysis does not make any sense. This analysis will be useless. So, I take this stability analysis, formulate the Routh array, and then try to get the conditions for kp and ki when the system is stable. So, if you do that, if you take from the first column, where when all the terms are positive, we can ensure the system is stable. So, from that I can see that this condition has to be 0, this condition has to be 0. So, taking these two conditions, I can ensure that when k is greater than 0 and when kp is greater than k by 10, the system is stable. So, when we need to identify or design this controller to understand the behavior, that means we need to also know the stability condition, that is the first condition. Second, what we saw in this problem is the effect of kp and ki on the error. So, if k is not equal to 0, the effect of the disturbance is nullified. But if the ki is equal to 0 and kp equal to 0, then there is no controller, the transfer function is 0, so you get infinity error, and this is useless condition. In this case, when k equal to 0 and kp not equal to 0, that is also a good scenario. So, when k not equal to 0, sorry, kp not equal to 0 and k equal to 0, only we are left with only kp function. It is like a normal steady state. So, what we get is a by kp. That means if you select good kp, you can reduce the steady state error due to disturbance. So, from this we can understand what type of controller can actually give you a good steady state error, so that when you are designing some simple controllers, you can analyze what gives you good performance. So, this kind of analysis will help us to understand when we are designing problems. So, the main purpose of learning this kind of analysis is in real systems, when you take a motor or when you take an elevator or when you take any modeling, when you analyze the system, you want to ensure that the steady state errors are also 0, and if there are any disturbances coming into the system, we also would like to ensure the effect of the disturbance is very small or the effect of the disturbance is reduced to 0. So, in this way we can actually make good design. So, that is the reason why steady state errors are very, very important in many control design problems. So, combined with stability, the steady state errors forms the basic requirements of the system. if the steady state errors are not 0, for any small disturbance the system deviates from the output, which is very inconvenient and which is very dangerous for real applications. So, with this one we have actually completed the problems. So, with this one we have completed the problem, 3 problems. So, these 3 problems will help you to understand in 3 different ways for from different application point of view. So, with this we reach the end of steady state errors. So, if we try to summarize what we have learned is, the most important is about our steady state error performance is only reliant on unity feedback system. So, if you do not have a unity feedback system, please convert into a unity feedback system. Suppose you have a feedback term here, change the system to unity feedback system, because the error constants are only defined for unity feedback systems. There are 3 error constant. K position is simple, limit s tends to 0, g of s. Velocity is derivative of position, so you get s into g of s. Acceleration is double derivative, so you get s square g of s. So, these 3 are very easy to remember. K position, no s, k velocity, derivative of g of s, k acceleration, double derivative. Position, you derivate, you get velocity, you derivate once again, you get acceleration, directly simple. Then error with respect to unit step is 1 by 1 plus k position, and error with unit ramp is 1 by k velocity, and error with the unit parabolic is 1 by k acceleration. So, if you remember this one, it is very easy, and this slide to me is most important because it summarizes everything here. Then the most other important is we learn that the steady state error also depends on the type of the system. So, these are definition for any system, and then when you apply these error definitions for various system types, the error performance is different. Now, coming to type of the system is the number of poles at the origin for open loop system. We call it the type of the system. If you have 2 poles, it is type 2. No poles at the origin, 0 type. So, what we see is, if there are no poles at the origin, I get error for a unit step, infinity error for ramp and parabolic. It is not really good. When you have 1 pole at the origin and the system is type 1, I get 0 step error for unit step, quite nice. Get finite error for unit ramp, infinite for parabolic. So, changing a system from 0 to 1 changes the error, a constant error, to 0 error. But if you go to type 2, when you have 2 poles at the origin, you get 0 error for step, 0 error for ramp, and constant error for parabolic. So, if you see, type 2 is much better compared to type 1 and type 0 system. So, increasing the type of the system will give you good steady state error performance. Type 3, most common used are type 1, type 2, but anything greater than 2, we know from the stability, more poles at the origin is not really good. It may actually give you problems with stability. So, more poles of the origin also make the system highly dynamic, and also it is not recommended. So, we do not go beyond type 3. So, we do not really go beyond type 1. So, preferred are type 1 and type 2. Many applications we like type 1 and type 2 systems. Type 3 also not generally recommended. Then last, we analyze the steady state error in the presence of disturbance. So, when we are analyzing in the presence of disturbance, we have 2 components. One is the error due to the actual input, and the error unwanted contribution from the disturbance. If we actually do the 2-stage analysis for the system with the disturbance input, we can also analyze the steady state error performance. So, with this I complete the steady state performance. With this we actually complete the part of the system, the error performance for our system. So, from the next part, I think after the steady state performance, we will be actually moving to root locus, and we are going to even other design problems. So, with this we complete the error analysis and the steady state analysis for our system. Next, we will be actually going through a very nice design technique that is in the frequency domain, that is called root locus, where we analyze how the gain affects the change in the location of the roots. So, this will actually start from the next week, that is the root locus. So, this is the end of this lecture. I would like to thank you for attending this class. Thank you. Kamsahamnida.